Let's consider a last case, which is a pretty complicated one. It's the vibration case. We have two boards. Now the upper board is not moving. The lower board can move, but with a very weird velocity, U times cosine omega t. So the lower board is vibrating, it's oscillating, right? Here x1 direction, x2 direction, or you can also say x direction and y direction. Here, if we write out the boundary conditions, what do we have? First, let's say d over dx equals to 0. Again, here we assume that the board is of infinite length. So everywhere is the upper stream and everywhere is the lower stream, right? You cannot distinguish between them, so the flow conditions do not change in the x direction. We can also assume that the flow is one directional. That is, we do not have the velocity in the x2 direction, only in the x1 direction. So what we are looking for is the velocity on the x direction. It can be a function of what? Of x2, or you can say y, and time. So if we write out the boundary conditions, it will be something like this. First, at this boundary, u0t, that is when y equals to 0, we are at this board, right? We should have the same velocity as this. So this thing should be u wall. When I'm at h, when I'm at this board, I should be not moving, right? So now with this assumption and the assumption of one directional flow, we can get the same simplified equation as the last case, which is the Rayleigh case, right? What we end up with is this equation. Du dt equals nu d squared u dy squared. This is the heat equation. Here again, how do we solve this? We surmise that the final form should be a form that looks like this. U is equal to capital U times something, times a coefficient. Okay, so what is that coefficient? First, let's transform the trigonometric functions cosine into a exponential form, because I prefer to work with that. It's a little simpler. So we know the Euler's formula, e to the power of I omega t is equal to cosine omega t plus I sine omega t, right? I bet when you were studying algebra, you learned complex numbers. So you should know this formula. Here, we see this thing is just what? It's just the real part of this complex number, right? So we can write this thing as the real part of this thing, ei omega t. So here, I can also write it as the real part of capital U. I forgot. Capital U times e to the power of I omega t. So here, U is equal to UW times something, right? So it should be U times the real part of e to the power of I omega t times some coefficient. And that coefficient can be a function of what? Can be a function of y, right? So this coefficient, we'll call it to be Fy. Now we can translate this to boundary conditions to make them boundary conditions on y, on F. How do we do that? When y equals to 0, that is, we have a F0 value here, right? F0 times this thing should equal to just this thing, right? So F0 should be equal to 1. But what will Fh be? Fh times this thing should give us 0. So this thing is not 0, then fh must be 0. Okay? So now we can plug in this relationship into our equation to get an equation on f. du dt, this thing, time derivative. Very simple. I just pull out I omega, right? And this thing, I just take the second derivative of f, because here y does not appear in the derivative. This part does not contain y, right? So if I take the y derivative, only this part is the derivative of this part is taken. So what I end up with, if I organize the form, then what we should get is something like this: f double prime from here, right? F double prime minus I omega over nu times f should give me 0. So this seems to be a not so hard to solve equation. It's a second order linear ODE, right? This can be solved by solving the characteristic polynomials. So let's do that. We assume that fy may equal to e to the power of lambda y. So to get lambda, we need to solve the following question, which is lambda squared minus I omega over nu equals to 0. So obviously lambda is equal to I plus 1 plus I omega over 2 nu. This thing. If we plug this back, we get the value of f. If written in a more elegant way, we can write sinh and cosh, sine hyperbolic and cosine hyperbolic, instead of using the power of e. Okay, so we can get something like this: a times sinh 1 plus I omega over 2 nu times y plus b cosh 1 plus I omega over 2 nu times y. Just a little reminder, if you don't remember, sinh x or sine hyperbolic x is just half ex minus e to the minus x, and this thing cosh x is half e to the power of x plus e to the power of minus x. So according to the boundary conditions, when y equals to 0, then we see when y equals to 0, this thing, the argument of sinh is 0. So sinh will give us 0, right? So we can get the b value from here. And then when we plug in y equals to h, we can get the value of a. Anyway, I will save the process and just give you the final result. The final result will be something like this: fy equals to sine h, sinh 1 plus I h minus y omega over 2 nu. And on the denominator is very similar: 1 plus I omega over 2 nu times h. So the only difference between the numerator and the denominator is here. Up here is h minus y, but down here is just h. Okay? So now we get our final result for u. What should u be like? U should be capital U times the real part of e to the power of I omega t times fy, right? 1 plus I, 1 minus I, 1 minus y over h. On the denominator, we have sinh 1 plus I, omega h squared over 2 nu. You see, we incorporated the h into the square root, right? This is for the sake of elegancy of our final form. So we get something like this. Well, this basically is our final result. But there are some points I want to emphasize. First, look at the term in the square root. Why did I say that it's elegant to incorporate the h into the square root? Because h squared over nu, it has some physical meaning. What is the dimension of h squared over nu? H squared over nu, h has the dimension of length, right? So it's length squared. What's the dimension of nu? L squared over t. So it gives us t, right? H squared over nu is the dimension, has the dimension of time. So it basically represents the time for the information of vibration down here to spread up here, right? H squared over nu basically represents the time for vibration to reach h. Time for vibration to reach h. It has this special meaning. Okay, so now let's consider two extremes. First is when omega h squared over nu is very, very smaller than 1. What does this mean? This basically is the relation between this time and this frequency, right? Omega is the frequency of the vibration. So if the product here is very smaller than 1, that is very near 0, then it means this time compared with this frequency is very small, right? So the time to spread is very, very smaller than the vibration period. Well, by mean period, I mean the cycle, okay? 1 over omega. So if this is indeed the case, then we can simplify our result, what we get here. U should equal to uy, should equal to capital U times the real part of this thing, I omega t. And here, when we see, when this thing is very small, right? So this thing is nearly 0, which means the argument of sinh is nearly 0. When sinh, well, let's just say the limit of sinh 0 is what? The limit of sinh 0. Well, maybe we can say the limit of sinh x when x tends to 0. What's this? We can maybe write it this way. Sinh x over x, let's say. When x tends to 1, this thing is 0 over 0, right? If we use L'Hopital, then we take both the derivative on the numerator and denominator. We get cosh x over 1. And cosh x at x equals to 1 is just 1. So this thing will give us 1, which means when x is very small, then sinh x should be of the same order of magnitude as x, right? So here, we can just use the argument of sinh to represent the sinh, right? So here what we get is this thing over this thing, right? 1 plus I, 1 minus y over h, omega h squared over 2 nu, 1 plus I, omega h squared over 2 nu. We see this thing are all cancelled. What we are left with is this thing times this thing's real part. But this thing is just a real number, right? So if we take the real part of this, we just get back the cosine. So what we are end up with is uw times 1 over y over h. Does this look familiar to you? Well, this is basically Couette. A little variation is here. It's the lower board that is moving, not the upper board, right? So here what the result we get is actually Couette. U over uw is a linear relationship. Couette. So another extreme case is when omega h squared over nu is very, very larger than 1. Then what will happen? Here, let's look at the asymptotes of the sinh. Uy is equal to u times the real part of this thing, e to this thing, times ei omega t minus omega over 2 nu times y. So if we take the real part of this thing, then what we'll end up with is this thing is a real number, and this thing is this thing's real part is cosine of this thing. So what we are end up with is u times e to the minus this times cosine omega t minus omega over 2 nu y. Well, the result may be not that important. What I want to tell you is this thing basically represents the spreading of wave, which has a wavelength of lambda equals to 2 nu over omega. This. And here we see this thing is very, very larger than 1, which means the h is very, very larger than lambda, right? You see the velocity profile of our final result doesn't contain h anymore, which means h here is like infinity, right? So here in this case, we are considering a case that is very similar to a Rayleigh, but instead of the lower board moving, it's instead of the lower board starting to move, now it's a lower board vibrating.